Hi, my name is João Pedro, and I will present the work Unsupervised Semantic Segmentation of aerial images with application to UAV localization. This work was produced by Brian Hane, João Pedro Clock, and Cristiano Leite. This presentation is divided into an introduction section, an explanation about the semantic segmentation pipeline, the experimental results section, composed by a description of the datasets, some examples, the semantic segmentation for UAV localization pipeline, a comparison with DSSNs, and finally the conclusion and acknowledgements. In recent years, semantic segmentation of aerial images has attracted a lot of research interest. Due to its many applications, such as terrain delimitation, surface change detection, water bottle segmentation, road extraction, and others. The current state-of-the-art in semantic segmentation is held by the Deep Semantic Segmentation Networks, or DSSNs. But there are a few problems with these networks. They require a labeled dataset, which can sometimes be very time expensive, and they are usually limited to the target domain from the dataset. This could be a problem for some applications, such as UAV localization, where the desired output is not known. Among the approaches to solve the UAV localization problem, a common technique is the template matching, which consists of comparing the UAV image with a source image. A problem that this technique faces is that many times both these images are from different sources, which could lead to mistakes. Furthermore, the template matching can be improved by the usage of semantic information, such as contextual information of the images. In order to deal with the uses of semantics in the UAV localization problem, we proposed a methodology of semantic segmentation of aerial images in which the targeted output masks are not known in advance. Therefore, we model the problem as an unsupervised learning problem and provide an application to a template matching-based UAV localization problem. This methodology does not require any prior knowledge on data or in parameter setting, and therefore is suitable for UAV embedded system implementation. We will start with the semantic segmentation pipeline. Here we have the UAV localization application pipeline. This pipeline will be explained later, but the semantic segmentation pipeline is given by this red shaded area. The semantic segmentation pipeline is given by an input image and 4 basic blocks: a preprocessing block, a superpixel block, a feature block, a semantics block, and finally, the output is the segmented image. We will now detail the individual blocks of the semantic segmentation pipeline. First, we start with an input image from the UAV. Then, we apply a smoothing filter capable of preserving the edges of the image. In this work, we used a bilateral filter. We then segment the image into superpixels using the slick algorithm. We define the number of superpixels based on the size of the image. Next, we extract both color and texture features from each superpixel. For the color features, we convert the image to 7 different color spaces, and for each color space, we extract 5 features of each superpixel: the mean, standard deviation, median, energy, and average gradient. As for the texture features, we use a Lang-Malik filter bank, composed of 48 filters. For each filter, in each color channel, we extract the same 5 features for each superpixel. These features are normalized both globally and locally, and since the resulting number of features is high, a PCA is also applied to reduce dimensionality, while maintaining 99% of the variance. Then, we have a semantics with post-processing step. We use the fuzzy semantics algorithm to clusterize the features into classes. To define the number of clusters, we evaluate the fuzzy semantics algorithm 30 times, and we use the knee point as the ideal number of clusters. Then, in order to ensure the best possible segmentation, we evaluate the fuzzy semantics for any exp number of times, and we use the partition of data with the highest Links-Harabase index. Finally, we construct a dendrogram with the resulting clusters and make a cut at 1/3 of its height, combining the clusters below. Finally, this will result in the semantic segmentation. An alternate version of this pipeline is also proposed, where we exchange the post-processing step for a classifier. Given that an image has already been segmented, a classifier can be trained using the resulting centroids, and superpixels from the following images can be classified among the centroids of the first image. Before showing the results, we will first show the datasets used in this work. We used two datasets. The first is a Brazilian dataset from the region of São Carlos. For this dataset, a georeferenced map is used along with 36 images taken from an UAV. We will also manually label both the georeferenced map and 10 images of this dataset into 4 different classes. In this image, we have the map and the classes with different colors. We also used a swirling dataset from the region of Província. This dataset is composed of the map and 1,594 images. Here we show some example images from the Brazilian dataset. Here we have the image, the semantic segmentation achieved by our algorithm, and the ground truth from the dataset in 4 different classes. Then we will explain the semantic segmentation for a UAV localization pipeline. This pipeline is composed of 2 different pipelines, one for the georeferenced map and one for the UAV image. The basic semantic segmentation pipeline is given by the red shaded area. There are a few new blocks in this methodology. First, there is the transformation step, in which we ensure that both the UAV and the map are in the same scale. Then we apply a histogram equalization in both images, and apply a histogram matching in the UAV image to ensure that both images are in the same space. The global normalization parameters of the map image are also applied to the UAV image. In the end of the UAV pipeline, we also fix the rotation of the image with respect to the map, and extract only the useful area from the rotated image. Finally, the images go through the template matching block, and the position is estimated. The template matching block have as input the map image and the semantic segmentation of the UAV image. The map is then divided into 10 by 10 blocks, and for each block, a patch with the same size as the useful area of the UAV image is cropped, and the semantics for this block is extracted. For each block, we extract the edges of the 2 semantic segmentations and calculate their correlation. With every correlation calculated, we have a correlation matrix, and then we estimate a normalized Gaussian distribution based in the entire matrix, using values above 70% of the maximum correlation value. We then select every value above 0.3, and they will compose a reduced search area for the UAV. Here we have the results for the position estimation experiments. In this experiment, we compared 3 different methodologies with our proposed approach in a template matching problem using the georeferenced map from each dataset and their respective images. In this map image from the Brazilian dataset, we have the original UAV route in black, our estimated route in orange, and the other results in different colors. As the table shows, we obtained better results using our methodology based in the reduced search area in both datasets. In order to ensure a good performance of our semantic segmentation methodology, we additionally made a comparison with some state-of-the-art DSSNs, in which we trained each DSSN with 1,000 random patches from the manually annotated map from the Brazilian dataset, and tested the performance in the 10 additional labeled images from the dataset. The results show that, even though our methodology does not surpass the DSSN segmentation, it's close enough to ensure good results in our proposed UAV localization application, with the advantage of not requiring any training in the targeted application. As for this experiment, both DSSNs took over 300 minutes to train, whereas our methodology took under a minute. Here we show some additional results in the comparison with the DSSNs. Finally, we conclude the presentation. In this work, we propose a novel semantic segmentation methodology that does not rely on deep learning and that is completely unsupervised. That is, it does not require any prior knowledge on the desired output and domain. We additionally proposed improvements in a template matching methodology, where we were able to provide the most likely region for an UAV within a geo-referenced map, also reducing the overall position estimation error through the usage of our semantics. For future works, we could explore additional uses for the semantic segmentation, such as deforestation detection or terrain delimitation. We could also provide better estimates for some of the parameters, that even though does not require any setting, they use poor estimates. And finally, we could integrate the methodology with embedded systems. We would like to thank Logi, CNPq, and CAPS for supporting this work. Here is my contact information, and the code for this work is public and available at this link. Thank you very much.